Welcome to this online course on multi-objective optimization with Gurobi. This course is brought to you by the Institute of Computer Science at Forth in collaboration with TwinODIS. We will explore how to model and solve decision problems that involve multiple, often conflicting objectives. You will learn the key concepts behind blended and hierarchical optimization, understand how priorities and tolerances affect solutions, and see how to extract deeper insights using tools like the solution pool. The focus will be practical and hands-on. By the end of the course, you will be able to build multi-objective models in Gurobi, configure them correctly, and interpret their results with confidence. Let's go through the contents of the course. We begin with a short recap of the basic Gurobi modeling concept under single-objective optimization. This ensures that the structure of a model, variables, constraints, objective, and optimization sense is completely clear before we extend it. Even in multi-objective settings, the solver still relies on LP relaxations and branch and bound, so this foundation remains essential. Next, we introduce the key points of multi-objective optimization. Here, we clarify what changes when multiple objectives coexist. We discuss conflicting goals, trade-offs, and how optimality must be reinterpreted when there is no single scalar measure. We then study the blended approach. In this method, multiple objectives are combined into a single weighted sum. This allows us to express trade-offs explicitly through weights, and the solver treats the resulting model as a standard single objective MILP. After that, we move to the hierarchical or lexicographic approach. Instead of combining objectives, we assign priorities. The solver optimizes them sequentially, preserving higher priority results while improving a lower priority ones. Finally, we examine degradation and tolerance mechanisms. These allow controlled relaxation of higher priority objectives, enabling more flexible trade-offs while maintaining a structured optimization. This sequence provides both conceptual understanding and practical modeling tools for multi-objective optimization in MILP. Let us now briefly revisit a very simple optimization example. The purpose here is only to refresh the basic modeling structure before we move to multi-objective concepts. Here the variables are xij, and they are binary, meaning they take values 0 or 1. Conceptually, each xij represents a yes or no decision, whether element I is assigned to element j. These are the decisions that need to be made. Next, we look at the constraints. They define how the system is structured and what its limits are. Together, these specific constraints resemble a standard assignment type structure. Then we move to the objective function. In this example, we maximize the sum over og and j of Cij times Xij. The objective answers the question, what needs to be maximized or minimized? Finally, the coefficients Cij are known parameters. They represent the value or benefit associated with assigning I to j. And along with the sets I and j are data we already know. Now that we have recalled the structure of a generic MILP, we move to how this structure appears inside Gurobi. Everything begins with gp.model. Decision variables, constraints, and objectives are always associated with a model object. The model is the container that holds the entire optimization problem. To define decision variables, such as xij, we use model.add_var or model.add_vars. These correspond directly to declaring variables in the mathematical formulation. To add constraints, we use model.add_conster or model.add_constars. These implement the algebraic restrictions, such as the summation constraints over sets I and j. To define the objective function, we use model.setObjective. This corresponds to specifying the maximization or minimization expression in the mathematical model. So this slide makes the mapping explicit. Mathematical structure on the right, API commands on the left. The architecture of the optimization problem remains the same. Gurobi simply provides the tools to encode each component precisely and systematically. Now, let's revisit the multi-energy optimal power flow system we had analyzed in a previous lecture. At the center, we see the power grid. It acts as the main electricity backbone, connecting multiple generation technologies and multiple types of demand. Electricity can be produced from hydropower, wind power, photovoltaic generation, and combined heat and power units. These sources feed into the grid and supply electrical loads, which are represented on the right-hand side. In parallel, we observe the gas infrastructure. Natural gas flows through the gas pipeline and feeds a combined cooling, heating, and power unit, labeled CCHP. This unit converts gas into multiple energy carriers simultaneously: electricity, heat, and possibly cooling. Heat and cold are distributed through a thermal network. There's also heat and cold storage, which allows temporal shifting of thermal energy. Similarly, electricity as storage is connected to the power grid, enabling flexibility in electrical balancing. On the demand side, energy is consumed in different forms: electricity for electrical loads, heat for thermal needs, and cooling for air conditioning. Some loads can be supplied either directly by gas-based systems or by electricity-based systems, illustrating coupling between energy carriers. From a modeling perspective, this is a multi-energy network flow problem. Decision variables may represent generation levels, energy flows across networks, storage charging and discharging, and conversion between carriers. Constraints enforce power balance, gas balance, thermal balance, storage dynamics, and capacity limits. Here we present a simplified concrete instance of the multi-energy OPF problem. The system involves two energy types, electricity and hydrogen. We have supply nodes, Detroit and Denver, and demand nodes, Boston, New York, and Seattle. Energy must be transported from supply to demand through a power grid, subject to line capacity constraints. The objective in the original formulation is straightforward: minimize total energy delivery cost. This is actually a standard minimum cost flow modeling. So at this stage, we are dealing with a classical minimum cost flow problem over a network extended to multiple energy carriers. We now make the network structure more explicit. Detroit and Denver act as supply nodes. Each one can generate both electricity and hydrogen. These supplies enter the central power grid. On the demand side, we have three cities: Boston, New York, and Seattle. Each city requires energy, and flows can be routed from either supply node through the grid. The colored lines represent possible transmission paths. Blue lines correspond to hydrogen energy type, while yellow lines correspond to electricity energy type. Conceptually, each arc in this network corresponds to a decision variable: how much energy of type E flows from node I to node J. This is precisely the structure of a network flow model. Here, we introduce the first layer of realism: line capacity limits. Each transmission line between the Detroit supply node and a demand node has a maximum allowable flow. For example, from Detroit to Boston, the capacity is 100 megawatts, from Detroit to New York, 80 megawatts, and so on. These numbers define upper bounds on the flow variables. In modeling terms, for each arc and each energy type, total flow must be less than or equal to the corresponding capacity. This is a classical arc capacity constraint in network flow problems. In the single objective version, these limits simply restrict the feasible region, so the solver searches within these bounds to find the minimum cost routing. This slide mirrors the previous one, but now for the second supply node, Denver. Just like Detroit, there is a limited line capacity from Denver to any demand node. So structurally, this adds another supply constraint to the model. This slide summarizes the transmission limits in tabular form. For each pair from and to, we specify the maximum allowable power flow. This table is essentially the data input for the arc capacity constraints in the model. In implementation terms, this is where we define parameter values that enter constraints of the form: flow from I to J is less than or equal to capacity IJ. The solver treats these as linear upper bounds that restrict feasible routing patterns. Now we introduce the cost structure of the network. Each connection between a supply node and a demand node has an associated transportation cost per megawatt. Importantly, costs differ not only by route, but also by energy type. So each arc in the network is characterized by two parameters: A, a capacity limit, which we defined earlier; B, a cost coefficient expressed in euro per megawatt. These cost coefficients directly define the objective function of the single objective model. The total cost is simply the sum over all arcs and energy types of cost per megawatt multiplied by the corresponding flow. This slide mirrors the previous one, but now focuses on cost coefficients for flows originating from Denver. Just as we defined route-specific costs for Detroit, we now specify the cost per megawatt for sending electricity and hydrogen from Denver to Boston, New York, and Seattle. Again, each arc is characterized by a cost parameter. These values directly enter the objective function. For every flow variable, total cost equals cost per megawatt multiplied by the corresponding transported quantity. The key point is that cost structures differ between Detroit and Denver. Some routes are cheaper from Denver, others from Detroit. This asymmetry is what makes the routing decision non-trivial. In the single objective formulation, the optimizer aggregates all these costs and selects the least cost combination of flows, subject to capacity and balance constraints. So at this stage, entire cost structure of the network is fully specified. Here, we summarize the entire cost structure in tabular form. On the left, we see transportation costs for electricity. For each pair of origin and destination, Detroit or Denver to Boston, New York, or Seattle, we have a cost expressed in euro per megawatt. On the right, we see the corresponding table for hydrogen. The same network structure applies, but the cost coefficients differ. Note that hydrogen transportation cost is generally higher than that of electricity. Now we formalize the core modeling elements. The main decision variable is flow of energy, E, from node I to node J. So for every energy type, electricity or hydrogen, and for every ordered pair of connected nodes, we define a continuous variable representing the amount of energy transported. This indexing structure is important. The index E distinguishes between electricity and hydrogen. The index I denotes the origin node. The index J denotes the destination node. This gives us a three-dimensional decision space: energy type, origin, destination. In addition, we define an inflow parameter at each node and energy type. If inflow of energy, E, at node J is greater than 0, the node acts as a supply node for that energy. If inflow of energy A at node J is less than 0, the node represents demand. This sign convention allows us to write flow balance constraints in a compact and unified way. At each node and for each energy type, total incoming flow plus local generation must equal total outgoing flow plus demand. So this slide bridges the graphical network representation and the algebraic model. We now have a clear definition of the variables and the supply-demand convention that will structure all constraints in the formulation. Finally, this slide presents the optimal solution of the single objective minimum cost formulation. On the left, we see the electricity flows. On the right, the hydrogen flows. Notice what is happening structurally. The solver is not trying to balance routes equally. It is purely minimizing total transportation cost while respecting supply limits, demand requirements, and arc capacities. Each decision reflects the relative cost structure we defined earlier. Cheaper routes are used first, and more expensive ones are only used when necessary to satisfy demand or capacity constraints. Algorithmically, this solution was obtained by solving a linear program. The LP relaxation here is exact, since flows are continuous variables. The solver simply optimizes over a convex feasible region, defined by balance and capacity constraints. This solution is optimal with respect to total cost. However, it optimizes a single aggregated objective, the sum of electricity and hydrogen costs? What if minimizing electricity cost and minimizing hydrogen cost are not perfectly aligned goals? Most optimization models we study initially are built around a single goal. For example, we minimize cost or maximize profit. The problem is defined around one clear objective function, and the solver searches for the best feasible solution according to that metric. However, real-world decision problems rarely involve only one goal. Very often, objectives conflict. In production planning, we may want to maximize profit, but at the same time, minimize late orders. Increasing production volume might increase profit, yet also create bottlenecks and delays. In workforce scheduling, we may want to minimize understaffed shifts, but also respect employee preferences. Improving coverage may require violating preferences, while respecting preferences may reduce coverage quality. The key point is that we cannot optimize all objectives simultaneously to their individual best levels. There's no solution that maximizes profit, minimizes lateness, satisfies every preference, and minimizes cost all at once. Therefore, decision-making becomes a question of managing trade-offs. And this is precisely the setting in which multi-objective optimization becomes necessary. When objectives conflict, the question is no longer simply how to optimize, but how to structure priorities. In many real decision problems, objectives are hierarchical. For instance, safety may come before cost, or service quality before efficiency. This means that not all goals are treated equally. Some must be satisfied first, and only then can we improve secondary criteria. At the same time, trade-offs must be controlled explicitly. If we allow improvement in a lower priority objective, we must define how much deterioration we are willing to accept in a higher priority one. Otherwise, the optimization process may produce solutions that are technically optimal but practically unacceptable. Multi-objective optimization, from a theoretical perspective, is about finding compromises between competing metrics. Objectives often pull the solution in opposite directions. There is typically no single solution that is best for all objectives simultaneously. Instead, decision makers must determine how objectives are prioritized or combined. Modern solvers, such as Gurobi, support this process directly. Multiple objectives can be defined explicitly, and priorities can be assigned to enforce lexicographic optimization, where higher priority objectives are optimized first. Additionally, tolerances can be introduced to allow controlled degradation when moving between priority levels. In this way, theory and implementation align. We move from recognizing conflicting goals to encoding structured priorities and controlled trade-offs directly within the optimization model. Now we turn to how Gurobi structures multi-objective optimization in practice. Gurobi supports three main strategies. The first is the blended approach. Here, multiple objectives are combined into a single scalar objective using a weighted sum. For example, we may maximize 0.7 times profit minus 0.3 times emissions. In this case, weights express the relative importance of each objective. The solver then optimizes one aggregated function. The second strategy is the hierarchical or lexicographic approach. In this setting, objectives are assigned priorities. The solver optimizes the highest priority objective first. Then it optimizes the next objective, but only in ways that do not worsen the higher priority one. This preserves the order of importance explicitly. The third option is a hybrid approach. Here, objectives can be blended within the same priority level while still maintaining hierarchy across levels. This allows both structured priorities and weighted trade-offs where appropriate. So these three strategies give us flexibility. We can combine objectives into one scalar, enforce strict priority levels, or mix both ideas depending on the structure of the decision problem. Now, let's discuss the key attributes that control multi-objective optimization in Gurobi. First, NumObj specifies the number of objectives defined in the model. This tells the solver that we are no longer working with a single objective, but with multiple ones that must be handled explicitly. Object number identifies the index of a specific objective. When setting attributes, such as weights or priorities, this index allows us to refer to each objective individually. Next, objn_weight defines the weight associated with an objective in the blended approach. When objectives share the same priority level, these weights determine how they are combined into a weighted sum. objn_priority is used in hierarchical or lexicographic optimization. Higher priority objectives are optimized first, and lower priority ones are optimized only within the limits imposed by the higher levels. Then we have objnreltol and objnabstol. These parameters allow controlled degradation between priority levels. Instead of enforcing a strict equality on higher priority objective values, we can permit small relative or absolute deviations when optimizing lower priority objectives. Finally, objnval stores the objective value of each objective in the final solution. This allows us to analyze how each criterion performs in the obtained compromise. Together, these attributes provide precise control over how multiple objectives are structured, prioritized, and evaluated within the solver. Once the theoretical framework is clear, the implementation follows a structured sequence. We begin exactly as in any optimization model. Define the decision variables and constraints. The mathematical structure of the model remains unchanged. Multi-objective optimization does not alter feasibility. It only affects how solutions are evaluated. Next, instead of specifying a single objective, we explicitly add multiple objectives. In Gurobi, this is done using the appropriate multi-objective interface, where each objective is defined separately. After defining them, we must decide how they interact. We can assign weights if we follow a blended approach, or priorities if we adopt a hierarchical structure. In some cases, we combine both ideas, blending objectives within the same priority level. Then, tolerances are configured. These parameters control whether lower priority objectives are allowed to slightly degrade higher priority ones, and by how much. This step is essential for managing controlled trade-offs. Finally, we optimize and analyze the objective values obtained for each defined objective. At this stage, the focus shifts from a single number to a vector of performance measures. In practice, multi-objective optimization is therefore an extension of the standard modeling workflow with additional structure to encode priorities, weights, and acceptable compromises. Let's now discuss on how multi-objective optimization is implemented in Gurobi. Every Gurobi model begins in a very simple state. It already contains one objective, initialized to 0. This is considered the primary objective. In single objective models, this objective can later become linear, quadratic, or piecewise linear, but initially it is just empty. There are two main ways to modify it. First, through the obj attribute. This allows us to change the coefficient of a specific variable directly. For example, setting x.obj equals coef adjusts how much that variable contributes to the objective. Second, through the setObjective method. This replaces the entire objective expression at once. It is the standard way to define a complete objective function, including the optimization sense, such as minimization or maximization. So before introducing multiple objectives, it is important to remember how Gurobi handles the default single objective and how we can modify it. Here we see two equivalent ways to define the objective in practice. On the left, we modify coefficients individually using the obj attribute. We create the model, add variables and constraints, then directly assign objective coefficients to each variable. Finally, we set the optimization direction and solve. On the right, we use setObjective to define the full objective expression in one statement. Instead of assigning coefficients separately, we write the complete linear expression and specify whether we minimize or maximize. Both approaches produce the same mathematical model. The difference is only in how we express it in code. This is useful to understand because multi-objective modeling builds on exactly these same mechanisms. Now, We extend this idea to multiple objectives following the blended approach. In this example, an energy operator must decide how much electricity to generate from coal, gas, and wind. The total demand is 150 megawatt hours, and each source has a maximum capacity. We define two objectives. A cost objective based on the production cost of each source, and B, an emission objective based on CO2 intensity. These two objectives are measured in different units, euros and tons of CO2. Since they are not directly comparable, we introduce weights, typically denoted W1 and W2. The blended objective becomes a weighted sum of cost and emissions. By adjusting the weights, we control the importance of each goal. The constraints remain the same, demand must be satisfied, and production must stay within capacity limits. So the blended approach transforms a multi-objective problem into a single aggregated objective where trade-offs are controlled through carefully chosen weights. In a multi-objective model, the key method is set, objective N. This method allows you to add or modify an objective inside a multi-objective model. Each objective is defined separately, and each objective receives its own configuration. Specifically, every objective has a unique index number, a weight if you use a blended approach, a priority if you use a hierarchical approach, optional tolerances, and a name. So instead of replacing the original objective, you extend the model with additional ones. Once defined, Gurobi manages them automatically according to the chosen strategy. Even in multi-objective optimization, there's only one global optimization direction. This is controlled by the model sense attribute. The model is either a minimization problem or a maximization problem. This setting applies to all objectives. You cannot directly minimize one objective and maximize another under different senses. However, you can achieve the same effect by using negative weights. For example, if the model is set to minimization, assigning a negative weight to profit effectively turns it into a maximization of profit. So the direction is global and flexibility comes from weights. For example, if you want to maximize profit and minimize emissions at the same time, you can keep model sense equal to grb.minimize and use a negative weight for the profit objective. By default, the model is set to minimization. In that case, the solver minimizes the total objective value. If you explicitly set the model to maximization, then the solver maximizes the total objective value instead. So there are three possible scenarios. In a standard minimization problem, model sense is set to minimize and the objective is minimized. In a maximization problem, model sense is set to maximize and the objective is maximized. In case of a mixed direction objectives, model sense is set to minimize. However, weights may also have negative values, which in essence treats corresponding objectives as if they are being maximized. As a result, the optimization direction is global and uniform. Mixed behavior is achieved through weights, not through multiple senses. This keeps the model mathematically consistent while still allowing realistic trade-offs between competing goals. When working with multiple objectives, each objective has its own set of coefficients. This is where the OBJN attribute becomes important. OBJN stores the coefficient of a variable for a specific objective function. Since a model may contain several objectives, you must specify which one you're referring to. This is done using the objNumber parameter. By setting objNumber to a particular index, you activate that objective. Then, when you read or modify OBJN, you're working with the coefficients of that selected objective. For example, a variable may have a cost coefficient in objective 0, and the same variable may have an emission coefficient in objective 1. These are completely independent. If OBJNumber equals 0, OBJN behaves exactly like the standard OBJ attribute in single objective models. So conceptually, OBJN extends the familiar single objective mechanism to a multi-objective setting without changing the logic, only adding indexing. In addition to variable coefficients, each objective may include a constant term. Mathematically, an objective can be written as a linear expression plus a constant offset. That constant is stored in objn-con. Just like with objn, you first select the objective using obj number. Then you can query or modify its constant term. If obj number equals 0, objn-con behaves like objcon, the regular constant term in a single objective model. Why is this important? Because in hierarchical optimization, even constant terms affect the evaluation and comparison of objective values. So Gurobi gives you full control, not only over coefficients, but also over the complete objective structure. Now we move to hierarchical multi-objective optimization. In this approach, objectives are not blended. They are ordered. The objn priority attribute defines that order. Each objective is assigned an integer priority value. Higher numbers mean higher importance. The solver works sequentially. First, it optimizes the highest priority objective and finds its optimal value. Then, it keeps that value fixed, or nearly fixed, and optimizes the next priority objective within that restricted solution space, then the next one, and so on. This means that lower priority objectives can never override higher priority ones. If two objectives share the same priority value, they are optimized together in a lexicographic manner at that level. By default, all objectives have priority 0, so you must explicitly assign priorities to activate hierarchical behavior. This structure reflects real decision-making processes, where some goals are non-negotiable and others are secondary. In pure hierarchical optimization, higher priority objectives are protected completely. However, in practice, we often want a small amount of flexibility. This is where obj-n-reltol becomes essential. Obj-n-reltol defines the relative tolerance that allows a controlled degradation of a higher priority objective when optimizing lower priority ones. Here's how it works conceptually. First, Gurobi optimizes the higher priority objective and finds its best value. Then, when optimizing the next objective, it allows the first objective to worsen, but only within the percentage specified by the relative tolerance. So instead of being perfectly fixed, it is protected within a defined margin. This mechanism enables small, controlled trade-offs. It prevents rigid solutions where tiny improvements in a lower priority objective are impossible, while still preserving the dominance of higher priority goals. For mixed integer models, both relative and absolute tolerances can be used. For linear models, only the absolute tolerance applies. Overall, obj-n-reltol introduces flexibility without losing hierarchical structure. It transforms strict priority into controlled priority. When we use hierarchical multi-objective optimization, objectives are solved one after the other according to priority. First, the higher priority objective is optimized. Then, lower priority objectives are optimized, but without completely destroying the quality of the higher priority one. This is where relative tolerance comes in. Suppose the best cost found in the first stage is 1,000. If we set a relative tolerance of 5%, we are allowing the cost to increase by up to 5% while optimizing the next objective, in this case, emission cost. That means the cost is allowed to go up to 1,050. In other words, we protect the higher priority objective, but we allow controlled degradation to improve lower priority objectives. This is a practical way to model trade-offs in real decision-making. Let's now discuss a concrete use case from the logistics domain. Consider a company choosing between delivery routes. Each route has a cost and a delivery time. We define two objectives. Objective 0, with higher priority, minimize cost. Objective 1, with lower priority, minimize delivery time. We introduce degradation using the obj-n-reltol parameter, stating how much worse the higher priority objective is allowed to become when optimizing the next objective. This way, instead of rigid lexicographic optimization, we introduce flexibility. We build and solve the model twice. First, with 0 tolerance. That means no degradation is allowed. Second, with a tolerance of 10%. The decision variables are binary, x1 selects route 1, x2 selects route 2. At least one route must be chosen. The cost objective minimizes 100 times x1 plus 110 times x2. The time objective minimizes 10 times x1 plus 5 times x2. Route 1 costs 100 and takes 10 units of time. Route 2 costs 110 and takes 5 units of time. After solving both cases, we compare which route is selected and how the results change when degradation is allowed. This shows clearly how tolerance affects the final decision. In multi-objective and mixed integer models, Gurobi may store multiple feasible solutions, not just the best one. Each stored solution has values for all objectives. The obj_val attribute allows you to retrieve the value of a specific objective for a specific solution in the solution pool. We can choose objective by using obj_number and solution using solution number. This is very useful when analyzing trade-offs, near optimal solutions, or alternative decisions, since it lets you analyze how each feasible solution performs across all objectives. In this example, we move to a slightly richer scenario. A logistics company must select exactly one out of 3 possible delivery routes. Each route has 2 performance measures, cost and the delivery time. We define 2 objectives. Objective 0 has higher priority and minimizes total cost. Objective 1 has a lower priority and minimizes delivery time. However, this time there's an interesting twist. Routes 1 and 2 have exactly the same cost. That means that, with respect to the first objective, there are multiple optimal solutions. Instead of stopping at a single solution, we will activate the solution pool. The idea is to capture multiple feasible or near optimal solutions and then analyze how each performs with respect to the secondary objective. The steps for addressing the problem are the following. First, formulate the hierarchical multi-objective model. Second, configure the model so that multiple solutions are stored. Third, retrieve the objective values for each stored solution using obj_val. And finally, compare the routes in terms of both cost and time. Let us now look more closely at the formulation of this example. We still have 2 objectives arranged hierarchically. Objective 0 has higher priority and minimizes cost. Objective 1 has lower priority and minimizes delivery time. There are 3 available routes and their costs. With respect to the first objective, routes 1 and 2 have equal cost. They are both optimal for the high priority objective. Because routes 1 and 2 tie on cost, the first optimization stage does not uniquely determine the solution. So instead of arbitrarily returning only one of the cost optimal routes, we can store both in a solution pool. Then in the second stage, when we look at delivery time, we can compare them. Between route 1 and route 2 has better time. So if time is the second objective, route 2 becomes more attractive among the cost optimal set. At this point, we focus specifically on the attribute obj_val. This attribute returns the value of a particular objective for a particular stored solution. When using the solution pool, the model may contain several feasible solutions. Each solution has a value for every objective. To retrieve a specific number, you need to specify 2 things. First, which objective you are referring to. This is done using the parameter obj_number. Second, which solution in the pool that you want to inspect. This is done using the parameter solution number. Once these 2 are set, model.obj_val gives you the corresponding objective value. So conceptually, the process is select objective index n, select solution index k, read the objective value for that pair. This allows you to build a comparison across solutions. For example, you can fix objective 0, which is cost, and loop over all stored solutions to see which ones are cost optimal. Then you can switch to objective 1, which is time, and evaluate how those same solutions perform with respect to delivery time. The important insight is that obj_val does not modify the model. It is a read-only attribute, since its purpose is analysis. Now we look at another useful attribute model, obj_name. When working with multiple objectives, Especially in larger models, objective indices alone can become confusing. Objective 0, objective 1, objective 2. These numbers are technically correct, but not always descriptive. The OBJName attribute allows you to assign and retrieve a name for each objective. This improves clarity and readability. For example, instead of referring to objective 0, you can name it cost, and instead of objective 1, you can name it delivery time. This becomes especially useful when you are printing results, you are analyzing values using obj_val, or you are presenting results to non-technical stakeholders. The workflow is similar to other multi-objective attributes. Finally, we look at the attribute model .numObj. This attribute tells you how many objectives are currently defined in the model. In a single objective model, this value is 1. In a multi-objective model, it reflects the total number of objectives that have been added using methods like setObjective. This is particularly useful when you are working programmatically. Instead of assuming that there are 2 objectives or 3, you can query numObj and then loop over them. This makes your analysis scalable and robust. If later you add another objective to the model, your analysis code does not need to change. It will automatically adapt. Conceptually, numObj gives you a high-level view of the model structure. It answers the simple but important question: how many objectives am I actually optimizing? Like OBJName and OBJNval, this attribute does not change the optimization itself. It is informational, but it is essential for building clean and reusable multi-objective workflows. Before we conclude, I have included a short list of references to the official Gurobi documentation on multi-objective optimization. It provides detailed explanations of blended and hierarchical approaches, objective attributes, tolerances, priorities, and practical implementation examples. I encourage you to consult it for deeper technical details and additional examples. Now let us briefly recap what we covered. We started from single objective modeling and moved to multi-objective optimization. We explored blended approaches with weights and hierarchical approaches with priorities and allowable degradation. We examined key Gurobi attributes related to multi-objective optimization, and we saw how to use the solution pool to analyze alternative high-quality solutions. The central message of this course is that multi-objective optimization allows us to model trade-offs explicitly and support better, more informed decisions. Thank you very much for your participation and attention.